Today we come to study the last three topics for applications of Laplace transforms. So the first one is system of linear ODEs. So we have seen examples of linear ODEs in one unknown function which can be solved using Laplace transforms. Now we can also have a system of linear ODEs with more than one unknown functions, and the derivatives of the unknown functions are dependent on the other functions as well. So they are a system of linear ordinary differential equations. Next is linear partial differential equations, where you have a function of more than one variable, an unknown function and of more than one variable, and you have partial derivatives, an equation which has partial derivatives with respect to some of those variables. Then you get a linear partial differential equation, and we will see that the Laplace transform is also applicable to solve these kinds of equations. The last one is linear difference equations and recurrence relations. These two are interrelated, and we will see also how to apply the Laplace transform to solve these equations. So first let us look at system of linear ordinary differential equations. So the first topic, system of linear ODEs. So an example of a first order system of first order linear ODEs, system of first order linear ordinary differential equations in two unknowns, say y1t and y2t. So we have two functions y1t and y2t which we have to find out, and this satisfy some differential relations. So the first one can be, let's say, y1 prime t equals a11 y1t plus a12 y2t, and y2 prime t equals a21 y1t plus a22 y2t. So the derivative of y1 prime is dependent on both y1 and y2, and similarly the derivative for y2 prime is dependent on both y1 and y2 as well. So now we can assume that some initial conditions, so the initial conditions for this problem is y1 0. So this is supposed to be valid for t greater than or equal to 0, and for the initial condition we take y1 0 equal to 0, and well, I can take some constant alpha, and y2 0 is some constant beta. So we assume all these functions, unknown functions, are continuous and the derivative is continuous and so on. So we will assume that y1 t, y2 t and y1 prime t, y2 prime t are continuous on 0 infinity. So continuous as well as of exponential order, continuous on 0 infinity and of exponential order, so that we can apply our Laplace transform techniques. So let's look at the transformed equation for this problem. Transformed equation. So for this we take the Laplace transform on both sides. So let's say for the first equation we will get, so let me denote capital Y1s. Y1s is the Laplace transform of y1t, and y2s is the Laplace transform of y2t. So for the first equation we will get sy1s minus y10 equals a11 y1s plus a12 y2s. Similarly, for the second equation we will get sy2 s minus y20 equals a21 y1s plus a22 y2s. Simple enough. This is just by the derivative theorem. This is by the derivative theorem. So now we can rearrange and we will get a system of linear algebraic equations in two unknowns y1s and y2s. So let's rewrite this. So the first equation, I am going to put all our y1 and y2 on the one side and the rest of the constants on the other side. So we will get s minus a11 y1s minus a12 y2s is equal to y10, which is alpha. And similarly for the second equation we will get minus a21 y1s minus or plus s minus a22 y2s is equal to y20, which is beta. So now we have a system of linear linear equations in two unknowns y1s and y2s. So we can apply Cramer's rule to solve this for y1s and y2s. So for y1s we get the determinant of the matrix alpha beta, and then you have minus a12 s minus a22 divided by s minus a11 minus a21 minus a12 s minus a22. So you will get a rational function in S. So the numerator is alpha times s minus a22 plus beta times a12 divided by s minus a11 times s minus a22 plus a12 a21. Sorry, there is a minus sign here, minus. Similarly, you can solve for y2s. Similarly, y2s is equal to the determinant of the matrix s minus a11 minus a21 alpha beta divided by the same denominator, and so you get beta times s minus a11 minus or plus again alpha times a21 divided by s minus a11 s minus a22 minus a21 a12. So now we get both our y1s and y2s are rational functions, and you can take L inverse y1t equals L inverse of y1s, and y2t is L inverse of y2s, can be obtained via partial fractions. So let us see an example, for a specific example. So we have y1 prime equals 3y1 plus 5y2 and y2 prime equals minus 2y1 plus y2, and the initial conditions are y1 0 equals 0 and y2 0 equals 1. So this is our alpha, this is our beta, these are our coefficients a12, a22, let me write in red, a12, a22, a21, and there is a 1 here, a22, and this is alpha and this is beta. So one gets y1s is equal to 5 over s minus 3 times s minus 1 plus 10, which can be rewritten as 5 by 3 times 3 over s minus 2 whole square plus 9, and so this is s minus 2 whole square plus 3 square, and similarly y2s can be written as s minus 3 over s minus 3 times s minus 1 plus 10, same denominator, and so you get here two terms. One is s minus 2 by s minus 2 whole square plus 3 square, and then there is a minus 1 over 3 multiplied by 3 over s minus 2 whole square plus 3 square. So now we have these terms. These terms are all well known. They are translated by 2, so there will be e to the power 2t, and they are either cos or sine functions. So let's write down the answer. So we have y1t, which is L inverse of y1s. This is equal to 5 by 3 e to the power 2t sine of 3t, and y2t equals, which is the L inverse of y2s, this is e to the power 2t cos 3t minus e to the power 2t by 3 sine 3t. So this is our solution. So therefore we can easily use our Laplace transform techniques that we know very well to solve such equations. Now let me give an application in physics. Application in physics and in particular mechanics. So here you have, this is called a coupled spring mass system. So here you will have masses connected by two springs. So you have one mass, let me call it mass with body with mass m1, and then there is another spring connected with another body with mass m2, and so we can again have a displacement and try to compute the forces according to Hooke's law. So in this case one gets the system of second order linear differential equations, system of second order linear differential equations. So let me write down what are these equations. So the first one, so let me call the displacement of m1 as x1 from the rest position, and the displacement of m2 let this be the rest position, and so the displacement is given by x2. So on the left hand side you will have m1 d2x1 over dt2. So this is the net acceleration, net force, and this is given by Hooke's law. So the body m1 will be pulled towards the left by this spring, the first spring, and let me assume that both springs have a spring constant k. So the first one will be pulled to the left by the first spring, so it will be minus k times x1. x1 has been the displacement from the rest position of the first spring. Now for the second spring, the displacement is given by x2 to the right, and then you have a minus x1 also to the right, because this is the rest position. So we will have we can consider x1 is in the negative of this rest position, so x2 minus x1, and then this first body m1 is pulled to the right by the spring, the second spring, so you will have a plus k x2 minus x1. Similarly, m2 d2x2 over dt2 is equal to minus k x2 plus k x1 minus x2. So this is now a system of linear second order differential equations, and we can have some initial conditions. For example, x1 0 can be 0, x1 prime 0 can be 0, x2 0 can be 1, x2 prime 0 can also be 0. So we can solve this kind of equation using these initial value problems, using the same Laplace transform technique. And as an exercise, find the solution to this system of differential equations. Let me call it 1. So find the solution to this system 1 using Laplace transforms. So this is a nice example where it can be applied to a physical problem. This is a coupled spring mass system. Now let's come to the second topic for this lecture, which is partial differential equations. So for this, we suppose we let u be a function of two variables x and t, be an unknown function which satisfies some equation. The equation can be written as some function set to 0, and this function f can take have x and t as variables, then it can have u itself as a variable, and then it can have the first partial derivative of u with respect to x and with respect to t, then it can have the second partial derivatives del u over del x2, del 2u over del t2, and then you can also have mixed partial derivatives, and then order 3 and so on. This is set to 0. So this function f is a linear function where f is a linear function in the variable u and all its partial derivatives. Meaning that if you take two functions u1 and u2, if u1 u2 are two functions and alpha beta are constants, then for example f of xt alpha u1 plus beta u2, and you can keep the rest to be the same. This is equal to alpha f xt u1, the rest are the same, and plus beta f xt u2, rest being the same. So it is a linear function in each of these variables u and all its partial derivatives, whether it is first order, second order, whether it is mixed or not. It is a linear, it satisfies a linearity property. So for example, examples of PDEs. So you can have del u over del t is equal to alpha del 2u over del x2, where alpha is a positive constant. So this is known as the heat equation that is studied in physics and thermodynamics. The second example can be taken as del 2u over del t2 is k times del 2u over del x2. Again, k can be taken positive, and this is known as the wave equation. So both these are examples of second order linear partial differential equations. These are second order linear partial differential equations. So all these kinds of equations can have initial values or boundary values. So initial values and boundary values, boundary value conditions are given to solve a PDE. So one can have, for example, in the first example, one can have u x0 equals 0 and u0t to be 1. So here we can have both constants, but also we can have functions of, when you are taking 0 in one of the variables, you can have the initial value as a function of the other variable. For example, you can put here ux0 equals x squared, or similarly you can put here u0t to be t. So these are initial value conditions for this heat equation, and one can solve this using Laplace transforms. So let's look at an example, solved example. So I am going to take the following PDE. So we have the differential equation x del u over del x plus del u over del t plus a u equals b x squared, where x and t are taken to be positive and a and b are constants. And we can have initial conditions. For example, x0 can be taken to be 0 and u0t is also 0. So to solve this, we will take the Laplace transform, take the Laplace transform on both sides. But here note that we have a partial derivative with respect to x as well as with respect to t. So we have to choose which variable to take for the Laplace transform. So I will take in the t variable with results in s variable with results in s variable. So now we will also assuming that the Laplace transform of del u over del x with respect to t, okay, is equal to the derivative of the Laplace transform of u with respect to t. Notice that when you take the Laplace transform with respect to t, the x variable still remains, and so we can take the partial derivative with respect to x of the Laplace transform of the original function. So in general, the Laplace transform of the function u x t with respect to t with the values output in the variable s, this is a function of both x and s. So we will assume that the Laplace transform and the partial derivative can be interchanged. So with this we will have x u, capital U x s, where capital U is our Laplace transform with respect to the t variable with results in s variable. Then we have the derivative del u over del t. So this is a partial derivative with respect to the variable in which we are taking the Laplace transform. So we can apply the derivative theorem here. So this will be s u x s minus small u x 0. So here when we are taking the derivative theorem, we can practically assume that x is a constant. So we can assume that this is a constant when we are considering the Laplace transform in the t variable. Similarly, if we took the Laplace transform in the x variable, we can make all the calculations supposing that our t variable is a constant. So this is by the derivative theorem. Then we have a u x s equals b x square over s, because there is still a 1 here which can be taken to be a function of t, or in fact bx squared itself can be taken to be a function of t, which is a constant function in t. So constant function will give you bx square over s. So now we will try to solve this. So I missed a derivative here, so this should be x del u over del x. So now this is a partial differential equation with respect to x, but it does not have any other partial derivatives with respect to s. So we can think of this equation as an ordinary differential equation in x. So we will try to solve this ordinary differential equation in x and see what we get, and then we have to take the inverse Laplace transform to find the original function u. So for this we can write x del u over del x plus s u. So I am dropping the variable names x and s because we are taking capital U. So this is a variable of x and s which I am omitting from the notation. So here this is just 0 by our initial condition, and then we have a plus a, so I will absorb it here, u x s equals bx squared over s. Now we can solve this partial differential equation by the method of integrating factor. So to employ our method, we will have to divide this equation by x on both sides. So we get this, And so the integrating factor is e to the power integral s plus a over x dx. So this is our integrating factor. So we can multiply on both sides and we will get del over del x of e to the power s plus a over x integral dx u xs is equal to bx e to the power integral s plus a over x dx. So the right hand side can be written as bx x to the power s plus a, and so this power and this power can be combined for x, and we can write s plus a x to the power s plus a plus 1. And now we can integrate on both sides, to get x to the power s plus a u xs equals b times x to the power s plus a plus 2 over s plus a plus 2. I missed an a, bx over s here, plus some constant of integration c, which implies that u xs equals b x squared over s times s plus a plus 2 plus c times x to the power minus s plus a. So now we can again use our initial conditions. Now we can take the other initial condition in t, which is u0t equals 0, and if we take the Laplace transform for this equation in t with respect to t with values in s, result in s, we get capital U of 0s equals 0. So now we can plug this in this equation 1. I'm not going to use it in this equation because there is a unbounded factor in x here, unbounded at x equal to 0. So I'm going to just plug in one previous step, which is where there is no unbounded factor in x. So I'm going to plug in x equal to 0 on both sides, and we get c equal to 0 because this will be 0 and this will also be 0. So this will give you c equal to 0. So this implies c equal to 0. So therefore we get u xs is equal to b x squared over s times s plus a plus 2. And now we can use partial fractions to get the inverse Laplace transform. So we get u xs equals bx squared 1 over s minus 1 over s plus a plus 2 divided by a plus 2. So in this case a plus 2 and a plus 2 will cancel out, and you will get immediately s 1 over s times s plus a plus 2. And now we can take the inverse Laplace transform, which will give you the solution uxt uxs. This is equal to bx squared over a plus 2. Again we are considering x to be a constant while taking the inverse Laplace transform. This is the inverse Laplace transform takes the function uxs, this is in variable s, and gives you back a variable t, and your function output function will be small u with variable x and t. So the first term is simply 1, and the second term is e to the power minus a plus 2 times t, and this is our solution for the PDE. So in this way we can solve linear partial differential equations using the Laplace transform technique by taking a derivative by taking a Laplace transform with respect to one of the variables and considering the other variable as constant, and we can consider the derivative theorem with respect to the transformed variable to find out the Laplace transform.